The plan for today is to basically go over quickly at a high level how we trained zembed-1. And then I will dive into evaluation results compared to other embedding models. Then we'll go over a very quick cookbook so you can see how to actually use it. So without further ado, I wanted to invite Nick to speak to the stage.
So I'm just going to go over real quick some of the training methodology. Now what's very interesting as well is I've added some reports for the Gemini training method and the Quenge training method, which I can also add in the chat as a comparison. Like this is the Gemini, and you can look at Quen as well. Because it's really good to get an idea of the way embedding models are traditionally trained in the literature. And what we found is that uniformly, they or universally, they all train with the InfoNCE loss. Um, if you're not familiar with InfoNCE, it's essentially a loss term that looks like this. Um, and it might seem a little complicated, but it's not that complicated. Because really what's happening is the numerator is your cosine similarity between the query and the correct document. That's all this sim function is. The cosine similarity between the query and the document. We take the exponent here, but honestly, because this similarity is usually between 0.3 and 0.7, this doesn't change all that much. So you can just treat this whole thing as like the similarity between the query and the document. And then the denominator is the the sum of the similarities with the queries and all of the other what we call negative documents. So you have positives and you have negatives, and you just put positives in the numerator and you put negatives in the denominator, and like that's the loss function. So basically, in order to improve this, and we're taking the negative here. In order to improve this objective function, we want the similarity with the correct document to be as high as possible. We want this numerator to be as high as possible. Um, and we want the similarity between the query and all of the negative documents to be as low as possible because they're in the denominator. So this is our objective function that we want to make as large as possible. Um, but the situation here that you might realize, or at least that we realized, because we discussed the Z-rank training method in detail, and our biggest innovation with Z-rank was using ELO scores. So, like pairwise comparisons let you finally sort the queries and the documents. Um, and this situation is extremely discrete. You just have positive and you have negative. But like what if you have a wide like you have like five potential positives, but you still want to sort them correctly? You kind of have like a continuous range between extremely relevant, very relevant, medium relevance, not relevance, super irrelevant. And this loss function, there's no way to work with this loss function in order to make that happen. And you can look at the way that it's trained. And the way that all of these models are trained are you sample a random document from the corpus. Um, you then ask an LLM to generate a query. And like this is now your positive QD pair because you made the query from the document. So like presumably it's quite relevant. Then you take the query and you do an embedding search. And you take one of those top 100 results from the embedding model as the negative. You just assume it's less relevant than the one that generated the query. And that's currently what goes into SOTA embedding models. So when we looked at this, we definitely knew there were improvements to make here by just making this training signal way more precise. Um, it took us a moment, but we had to look at this formula and figure out what we would want it to look like if it was soft targets. And one thing we realized is that this equation is identical to one of the most well-known loss functions in all of machine learning, which is KL divergence between the similarities and essentially a one-hot encoding of the correct answer. If you look at this, KL divergence is exactly what LLMs use when they're learning the next token. Like, and like this here is supposed to be like the previous tokens and the tokens that the LLM wants to return next. And this array here is just a one-hot encoding of the actual token that occurred next. So when the big labs are training LLMs on the whole internet, The goal is KL divergence between what it's currently outputting and like what it should output. But this is a one-hot encode. Why does this need to be a one-hot encoding? It doesn't need to be. Like we can just make this the ELO scores. Like we can change this to have a much more fine-grained signal. Like, oh, this one is 2.4, this one is 1.2, this one is 1.0.4. And then we can even go into the negatives here. Actually, I'm writing this in logit space. So more technically, this is a one-hot encoding of like infinity, negative infinity, negative infinity. But then you just take like the softmax of it, which gives you this. So if we go back to the logits, which are here, these are the logits that we can train from. And beautifully, it's the easiest possible way to get logits because we released zrank 2. So we can just use zrank 2 to give us the logits. And now this is our training signal. And the question here is how smart could we get this model? Before we even start training, we can look at performance of various embedding models on our internal benchmarks. And it's important to use internal benchmarks. We'll release a blog post on this as well, but the comparisons are very, very different than what you see on public benchmarks. Um, there's just a big problem where if you look at the results from the embedding models on public benchmarks, they're clearly picking the ones that were marked as correct, even though there are a lot of other documents that are more correct. And you can even do this with an LLM. Like you can ask you can even just rescore public benchmarks, like telling an LLM like, oh, which document is the most relevant, and it will just pick different annotations. So actually, a lot of our private benchmarks are simply taking a public benchmark and having for each query Gemini like go through every single document in the entire corpus and scoring it. Now this just gives brand new annotations that aren't the same ones that everyone is using. Um, and then interestingly, a lot of inversions happen. You do see models like Quen get pushed down by this scoring method. Voyage does better than most on something like this. Um, Along with the GINA embeddings, given that this is a 0.6b model. And OpenAI, Text Embedding 3 Large, and Voyage are basically the two SOTA models that existed before we were starting to train Zembed. And here you can see zrank. And this is by zrank doing a linear scan, like literally just taking the query and then looking at all of the documents. Obviously, this is too expensive to do in production, but we can see the massive score boost. It correlates way better with what the correct answer is. Um, and now our goal with distillation is to be able to train a model that is basically somewhere in the middle here. We want something, it's not going to be able to achieve the full zrank, but there's an enormous like 13% recall gap. I recall at 100. There's like 13% more documents that we could be pulling. So we definitely want to pull those. And now this is the discussion of our loss function. We're simply generalizing this to soft targets. And quite simply, what we did was we pulled an enormous corpus of queries and documents, literally like over 50 million queries, from basically processing Common Crawl at scale, which itself takes like thousands of hours of CPU compute time. But once you have those, you can then embed them all, take the top 10, score them with zrank, and then you have the targets to work with. And fantastically, we'll just show the results, but it worked astronomically well. Like just like that, zembed-1 with this loss function and our training methodology, zembed-1 immediately just does dramatically better, more than 7% recall at 100 better than all of our competitors on this benchmark. There were even two stages, pre-training and fine-tuning. I can try to get the pre-training graph.
And yeah, you can see that zembed-1 is like almost is like approaching a cross encoder. Like zrank-1 small is our uh, smallest cross encoder or re-ranker, and it's like extremely close.
Yeah, it really gives you the power of the re-ranker. Like our entire goal when we were iterating on especially post-training and the loss function is to get the embedding model to be as close as the performance of like literally scanning your entire corpus with a re-ranker. Because that's the whole point. Like you wish you could just scan the whole corpus with a re-rank. It's just too expensive. So inevitably you just want your embedding model to approximate this as best as possible. I can even come in here and show a graph of how well it was able to converge on the training signal, because it's really quite surprising. Yeah, this is a scatter plot between our re-ranker and our embedding model as we're training. And you can see here at the beginning how obviously in the first couple training steps, the embedding model is just outputting completely random numbers. It has no idea what it's doing. But we have our training targets, which are all of the extremely high quality scores provided by the re-ranker. And you simply give it time, and this will eventually converge to almost one. Like there's actually very little limitation here on the training data. Um, really all of the magic that went into, like, our entire team, the research team working for, like, over a month on this, went into making the data as collected, from the public internet as diverse as possible, which is very difficult, because if you sample random data from the internet, you kind of get random garbage. Like, that's great for pre-training, but when you actually wanna post-train into a SOTA model, you really need to you want to like curate the entire collection of PubMed for medical queries. You want to curate the entire collection of court opinions and stuff like that. They're like 20 million court opinions in the United States, and you want to be able to use that for legal research. So everything really comes down to the data mixture and making sure that as long as your data mixture is including all of the possible things that people could want in production enterprise use cases, then you're going to get this convergence with Z-Rank, and then you're going to be able to generalize that to all of the possible use cases that people might have.
One question is maybe, is it at all possible to completely match the performance of Z-Rank 2?
I am bullish that we could have a zembed-2 on the roadmap that closes this gap a little bit. We'll never One thing we found is we truly can't approach exactly the performance of the re-ranker, because there are always there are always two aspects when you're training a model. There's like in domain and there's out of domain performance. And then there's even training data performance. Um our goal with the data mixture, like I said, is to try to get all possible things that people might ask into, like, as close as possible to being in domain. But if you really want to ask what's the theoretical possibility, you should look at convergence on the training data itself. And if you see here, even as we get to step like 13,000, there's highly diminishing returns on the correlation. And if you graph this, it's clearly reaching an asymptote. We found even training to like 50,000 or 60,000 steps, it doesn't really progress that much past like 0.93. And the thing with this correlation coefficient is you can model this as noise. Like if you take little vertical splices of the target, like imagine the correct answer is like between 0.05 and 0.06. So you're taking this vertical splice. Well, the correct answer is in this range, but the model in this vertical slice is outputting a normal distribution here. Like if you take the splice and graph a histogram, you're gonna see a Gaussian distribution. And this is the noise of the model. This is the model's inability to perfectly predict the target. It's predicting it with noise. So you can actually go back and measure that noise in your training data, and then look at the recall at K graph by just simulating the noise. Meaning we take the Z-rank 2 scores, we add a little normal distribution noise to all of the logits, and just see how much that degrades the performance. Um, and we can add a graph of that offline, but the graph of that does look somewhere around here, and I would say that measures the like absolute maximum you could ever get with an embedding model, because if it can't learn it in training, it's literally sitting here training on exactly this data. So this is literally like overfitting. I mean, you're overfitting on the internet, which is like highly generalizing, but like the fact is if you can't surpass this boundary of this correlation of like 0.93 even on the training data, you're definitely not going to generalize to out of domain evals. Like these are just completely out of domain evals, so you're not going to beat this correlation coefficient. One idea that we have is potentially sparse embeddings, like increasing the dimensionality. The dimensionality was like 50,000 or 100,000. This correlation could potentially be unbounded and like not reach its asymptote that it's reaching, which would close the gap here. Yeah. One thing that super surprised us in the research was this graph. This is pre-training, meaning before we made the specialized QA data sets over PubMed and court opinions and stuff like that. This pre-training is just from queries and documents out of Common Crawl. scraped at scale. And this like this is honestly incredible. Like we immediately reached SOTA in just the pre-training stage, and then we got an extra like 5% boost in post-training. I think this shows the power of like the training distillation method itself. What this is showing, I can actually change the recall at K. What we do is we have our evaluation data, which is 1,180 queries across many different domains. It's like 200 queries per domain. And we like recall at K, there are multiple ground truths per query. Recall at K is the percentage of ground truths obtained by the model at that K value divided by the total number of ground truths. So if we look at the raw recall at K, we see a graph like this. This is just the raw recall at K. Um, because like within each K region, there's like, imagine this is the mean here. This is like the baseline, is like the average between all the models. It's just easier to observe the recalls if you look at like a delta recall at K. And here I just clamped like OpenAI text embedding 3 large to be the baseline, and then everything is being compared recall at K against the baseline. But these are the raw recall at K graphs. See, the difference is that on the low end, you get like 60% recall, and at the high end, you get like 80% recall. I don't know if that answers your question.
We have questions about the packages that we used. We might not mention compute and things like that, but do you want to talk to the ML pipeline? Yes, we use PyTorch.
Yep. Yeah, we don't use too many dependencies. Like our dependencies are only 2 libraries, LanceDB and PyTorch. And Lance is just for having all of our data in S3, and being able to randomly shuffle it for the training process, and then the training is just raw PyTorch. Oh, there's Hugging Face transformers for experimenting with the various base models because they provide that out of the box, which is great. Yeah, we have some like modifications to the loss function for like bias and Matryoshka and stuff like that. Um, like the core ranking loss is this one.
So I'll quickly go over some of the evaluation results in terms of accuracy, but also latency. I'll also talk about concrete evaluations against Voyage because I know that that was a question that was raised in the Discord. And yeah, I encourage you to check out this blog, which contains all of this information. So this graph basically allows you to look either at the absolute recall at K for different embedding models. Here we have Voyage 4 Nano, which is fully open source. We've had to have a different evaluation strategy because of the terms of use of Voyage 4 on AWS. So you can check out, just like we saw before, the relative performance, and you can compare to whichever embedding model you are currently using. So if you're currently on Qwen 4B, you can look at all of the models that outperform and underperform for this specific model. And we're also going to release more heads-to-heads comparisons against different other embedding models. We started with Voyage 4, but you can expect to see more. So you can have like a more fine-grained evaluation on each of these models. We worked a lot on our speed through quantization. So another benefit from using this model through our API is that you're going to get a much lower latency compared to other APIs. Namely, we've heard OpenAI's API that can get pretty slow. We also offer different embedding dimensions. We're going to have a whole blog post about that because we've explored Matryoshka representation learning and we decided actually to move away from it. All of the literature mentioned that there was no degradation with Matryoshka, but that was not our experience. So yeah, we're going to release a Matryoshka is dead blog post, so you can expect to see that soon. An interesting other vertical here is the multilingual performance. So we had a very similar matrix like this for our re-ranking models. And it's very interesting to see the degradation of some of these embeddings when you look at basically like cross-language queries and documents. So here you can see the query language, and here is the document language, and you can look at the degradation compared to purely English to English. So this is what zembed-1 looks like. But if you look at, for example, OpenAI small, it's a lot worse. You can also look at the percentage degradation from English. So this is like the relative degradation that you can see on other languages. So I receive a lot of, questions around, oh, how well does it do on X, Y, and Z language? So at least for those represented here, which are the most common, you should be able to have a clear number depending on the queries and the documents that you usually have and that your users are usually asking questions with. We also have this fun little UI here where you can basically look at the best deployment option and configuration depending on what you're trying to optimize for in this triangle of accuracy, speed, and cost. So you can go ahead and play with this. So depending on whether you want to use the zero entropy API, whether your vector database supports quantization, and how much you want to, have a trade-off between the maximum accuracy or really trying to minimize the cost as much as possible. You will basically have different options in terms of the dimension of the embedding, which is obviously going to have a footprint on the storage costs, and the type of quantization that we would recommend. So here are all of the possible combinations and configurations, and you can see basically the difference, like basically the recall trade-off that you will make depending on, again, the quantization and the dimension of the embedding. So this is the baseline with basically float 32 and the biggest embedding dimension, and you have all of the different configuration, and you can see how much recall you're losing, but how much storage costs you're going to save on your vector database on the other hand. So we already went over how we trained Zembed. I'm going to stop for questions and also mention that we have this spreadsheet where you can see like more detailed and fine-grained evaluation for all of these models on public and private data sets. And that gives you a sense of how well we perform on different verticals, which is also something that I get asked a lot. So for people asking whether zembed-1 outperforms Voyage 4, the answer is yes, according to our own evaluation, but also, as I mentioned before, this is also confirmed by the agent set evaluation. You can read, they have a whole blog post that explains more thoroughly on how they perform this evaluation as well. So I'd encourage you to check that out as well. So very similarly, you can look at the relative and absolute difference between us and Voyage 4. It is the best embedding model after zembed-1, according to our tests. So the way that we performed this evaluation was across 22 data sets, and we tried to be as broad as possible on the different verticals. So those are the different verticals that we evaluated. So technology, enterprise, healthcare, finance, and all of these other ones. And we try to have multiple data sets when possible. And this is what the delta NDCG at K looks like on these data sets. And we basically outperform on a majority of them, actually on 18 of them. But the best thing is that not only is it more accurate, but basically, I don't know if people here have tried using the Voyage 4 API, but we, at Zero Entropy, we really try to put a lot of effort also on the performance engineering and making sure that the latency is also acceptable for you even at a high QPS. But this is what basically the graph for the P50 latency looks like for different QPS numbers. So we're very proud to have this pretty low latency even as QPS increases, which is not the case for the other embeddings. So if latency is an issue for you, definitely check this out. This is another interesting experiment that we ran, where we basically wanted to take public data sets and try to modify them either on the query side or on the embedding side slightly, just to see how well that would impact the performance of the model and try to test for like overfitting on these benchmarks potentially, but more generally try to replicate what prod data looks like, which is never as clean as what you can see on the public benchmarks. So we did this funny experiment where we added an irrelevant statement to the query, which is basically this random water bottle flipping contest. So we basically just added that to the queries and tried to see what was the degradation like on, I believe this was on CureV1, which is a public healthcare related data sets. And the conclusion of that experiment is that the degradation on Voyage 4 is 5 times larger than zembed-1. Of course, we also saw some degradation on zembed-1, but it was much more contained than Voyage 4. So yeah, those are what the graphs look like. So yeah, the conclusion from this experiment, and we're basically running more experiments with translating the queries to multiple languages and adding other types of perturbations to the queries and the documents, just to try to test what that would look like on different embedding models. So we did it for Voyage 4, we'll do it for more models. But it's pretty interesting to see that, yeah, even just like a very short and small change to the query can have like such a drastic impact where a large number of query documents pairs were actually affected. We also ran another comparison where we basically wanted to do pairwise comparisons between like a query and 2 documents. And more specifically, this is the interesting graph, looking at when basically Zembed and Voyage 4 disagree on the ranking between the 2 documents, like document 1 and document 2. And we basically asked Gemini, multiple models, Gemini, Grok, and GPT, to decide on a side, to decide which embedding model they think actually is correct. And we see a pretty large gap between Zembed and Voyage, where the LLMs tend to agree with Zembed more than they agree with Voyage. And on a listwise comparison, we see also a pretty significant difference, with more LLMs preferring Zembed over Voyage 4. We don't have multilingual comparisons yet, but this is another experiment that we're currently running, where we take the queries and we translate them to a bunch of different languages without changing the QRLs, obviously, and try to see how much that degrades the performance of the different embeddings. So we'll be posting that as well. So if multilinguality is important for you, this should definitely be helpful to know. Yeah, we would absolutely love to have you guys, your feedback on this model. This is the actual best evaluation possible, and just to get feedback from you. So please try it out and let us know what you think. Okay, well, thanks everyone for joining. Feel free to continue the conversation. And yeah, we'll see you at the next Tech Talk.